Hello, everybody, and welcome to our second unit on gas laws. In this unit, we are going to focus on what is known as the ideal gas law, and then we are going to do some gas stoichiometry. So we always know stoichiometry is my favorite, so I'm excited to get back to that. So let's get started with what's known as Avogadro's principle. You should remember Avogadro from earlier in the year when we talked about Avogadro's number. And remember, that was 1 mole of anything has 6.02 times 10 to the 23rd in it. Well, one of the ways that Avogadro actually we got to that number was through the experimentation of Avogadro, and he did a lot with gases. And Avogadro's principle states that at equal temperatures and equal pressures, if you have equal volumes of gases, all right, so same volume under same conditions of temperature and pressure, those gases will also contain the same number of molecules. All right, regardless of what the gas is, you will have the same number of molecules of that gas. We call this the molar volume of a gas. And this is an important one, and this is why I have it starred. At STP, remember standard temperature and pressure, 1 mole of any gas, regardless of what that gas is going to have a volume of 22.4 decimeters cubed. Remember, a decimeter cubed is the same thing as a liter. All right, there's going to be a lot of different conversion possibilities for you in this unit, so really have to make sure of those units and double check those. A decimeter cubed is the same as a liter. All right, so now we are going to put all of these variables into one equation. Now, this next slide just shows you how we end up doing that. So this is not something that you guys need to memorize by any means. All right. Not that you're memorizing anything now, but you know what I'm talking about. Okay. The ideal gas equation is PV is equal to nRT. N stands for your number of moles. In order to relate pressure, volume, temperature, and the number of moles, we need a constant. All right, that can relate all 4 of those variables. We call that constant R. It is the ideal gas constant. And I'm going to show you one way to calculate that. You're not going to have to calculate this. The R will always be given to you. But if we use this equation and solve for R, putting in standard pressure, standard temperature, and Avogadro's principle, which is that 1 mole of any gas is going to have a volume of 22.4, we get this constant, all right? 8.31 decimeters cubed times kilopascals over moles times Kelvin. Okay, so a couple things about this gas constant that you have to be careful of. Anytime you use it, your volume must be in decimeters cubed, which is a liter. If you're using 8.31, your pressure must be in kilopascals. If you have a pressure that's millimeters of mercury, it's another gas constant. If it is atmospheres, it's another value. All of those will be given to you, and they are on the practice sheet that you will do after these notes. Okay. Temperature, because this is a gas law, will always be in Kelvin. So remember, that has to be converted. All right. I believe in the next slide of notes, let me just check really quick. Yep. You've got a couple practices where you're just going to be plugging in those numbers. So if you want to pause the video now, you can go on ahead and try those. All right. Okay, so let's look at these practice, okay? What pressure is exerted by 4.5 moles of gas in a 198 liter container at 8 degrees? Again, we're using the ideal gas equation. PV is equal to nRT. That's going to be the important equation for this unit. So really, always write that down as much as you possibly can. If you notice in my problems, I almost always write it first before I do anything else. I've only given you so far the R having to do with kilopascals. So that's what we're going to use for these notes. Again, always checking on your practice sheets. All right, so what pressure? So I'm going to solve for P. I like to do my algebra first, solving, putting my variables in, and I get about 53.1 kilopascals. All right, let's look at number 2. Number 2 took a little bit more work because it's 2 steps. What mass of oxygen gas will occupy a 450 ml flask at 11 degrees Celsius and 66.7 kilopascals? I'm asking for mass. Now, nowhere in our ideal gas equation do we have mass directly, but we do have moles, and moles is an amount of our gas that we can easily convert to grams. So sorry, this is bad handwriting, but that's N. So I'm solving for moles. and I plug in all of my values, making sure I, change Celsius to Kelvin, all that good gas law stuff. I end up getting about 0.0127 moles of oxygen. All right. Then I'm going to convert those moles of oxygen to grams using the molar mass, the mass from the periodic table. This is a good time to remind you when we say oxygen gas, nitrogen gas, chlorine gas, please remember your diatomics, all right, because those do come up a lot because they are diatomic gases, and this is our gas unit, so don't forget those, all right? Okay, next up, we're going to manipulate PV is equal to nRT to allow us to get a couple different things, all right? Using the ideal gas equation, we can determine the molecular mass, also known as the molar mass. I will ask you using both terms as any textbook or any, AP problems pretty much would. So just know that those two are interchangeable, all right? We know from our work since we were doing this in October that the number of moles of a substance is equal to the mass divided by the molar mass from the periodic table. So what I've done here is I have my ideal gas, PV is equal to nRT, but instead of N, all right, instead of moles, I'm putting little m over big M. Little m is the mass of your sample that will be given to you in the problem. Big M is your molar mass. That's what we're going to be looking at. All right, so let's look at this example because you can already see my work here. So this is the equation when looking for molar mass, capital M, molar mass, is equal to little m, which is going to be a mass sample. That's going to be in grams, RT over PV. So what is the molecular mass of a gas if 150 mils has a mass of 0.922 grams at 99 degrees Celsius and 107 kilopascals? All right, great. Well, I just plugged in all my numbers. All right, making sure I'm doing my proper conversions. Okay, 150 mils, changing those into liters. Don't forget, when you're dealing with R, it's always in terms of liters. And then when you solve for this, you'll get a number always over the number 1 because you can't have a molar mass less than 1. And in this case, our molar mass is about 177.6. The label for molar mass will always be grams per mole because using the R, that's what you end up getting or you're left over with after everything divides out. Okay. There's one more manipulation that we can do to the simple PV is equal to nRT, and that is solving for density. We know density is mass over volume. Well, if we look at this equation here, we have mass, we have volume, play around with the algebra a little bit, and you can solve for density problems. Okay, so density is mass over volume. I manipulated my PV is equal to nRT. So mass over volume is equal to your pressure times your molar mass over R times temperature. So if you'd like to pause your video and do the next example problem, this would be a great time to do that. Let's go on ahead and take a look at this answer. All right, I want mass over volume. So I'm going to put in my pressure times my molar mass over my gas constant times the temperature. And I get a pressure here of 1.68 grams per liter. Now grams, because I've got the gram here from the molar mass, all right, liters are going to be left over after everything else cancels out with the R constant, okay? And then you'll have your unit of grams per liter. All right, fantastic. This is the end of our first part of notes for this unit. So right now what you should do is go into the modules and work on the first practice sheet for this unit. And then this video will continue on to the second portion, but this is a good place to pause for day 1. All right, have a great one.